Sorry. Welcome back, students. Hope you're listening here. And I hope I unmuted my audio and it's working. I guess it is. Sorry about that. Okay. So now that you've done the calibration of your calorimeter, you're ready to carry out the actual chemical reaction we're interested in. You can look at your next data sheet, which is on page 38. Now, of course, you have received a file that has a filled-in data sheet. Oops, right, that's not it. I had put out the wrong data sheet in there. I'm sorry about that. Here it is. This is the one that you're going to do. So you are going to be studying the chemical reactions of a metal with HCl and its metal oxide. All right. It's very important that you remember that you are being given this data. Some of you are studying the reaction of magnesium. Some of you are studying the reaction of calcium, and of course, their corresponding oxides. So please bear in mind which of the two metals is in your data set, okay? So once more, as the video by Dr. Perot illustrated earlier, you will have a calorimeter with a solution of hydrochloric acid at a measured temperature. You're going to add a sample of either the metal or the metal oxide, and then you start stirring and measuring the temperature every 30 seconds, every half minute, and that'll be recorded in this table here. All right, so that's where we're going to be. And so let's come back here for a moment. All right, and let's go see what this will look like in our reaction system here. All right, so in my case, I am going to go over a reaction of magnesium. Again, some of you, it benefits you because you will get magnesium also, although your data will be different. So the reaction of magnesium is in there. Again, we let this reaction happen inside the calorimeter. And then what we do is we are going to record the temperatures. And I'm going to put them here on an Excel spreadsheet again, where I can see the temperature every half minute. And then as we did in the previous lab or the previous part of the lab, we're going to put this on an Excel graph. We're going to plot the temperature against the time. Now, in this case, what we notice, or we might notice, is that there's an initial climb, and after a while, it kind of settles, but it starts dropping off towards the end. You can see there's a slight drop in there. Well, that is because our calorimeter is not perfect. All we have for a lid is a piece of aluminum foil that by this point might be quite torn up because of the thermometer we inserted and all the stirring that we've done. And so there is an escape of heat through the calorimeter into the air around, and that's why the temperature drops. So what we'd like to do is we would like to be able to show, okay, what was the temperature that was reached by the reaction. So what we can do is we can take a trend line here, as you can see it there, and project it out. It's slightly slanted. Let's project it out and see how far that would have reached by reading its projection onto the y-axis, which is essentially the intercept that is given by this equation over there. And in this experiment in particular, we find that that final temperature was 38.0 degrees. So that would have been the maximum temperature. Notice that the graph landed, actually started at 39. Many times what's going to happen is your actual final temperature might end up being higher than any of the values that are in your data, because as it projects upwards, it reaches a higher temperature. Not so in this case. So we'll take what it says here and we're going to work with that, okay? So let's go ahead and come back to our to this same slide here, but instead I'm going to go to our doc cam here. So what we're saying is that we landed at a temperature here. We're going to say the final temperature here was 38.0. Okay. Now let's set up our experiment. All right. So let's come back here and let's look at our PowerPoint once more. and let's see what ended up being the experiment itself, all right? So here is the reaction again, and in this particular experiment, the student used 0.4817 grams of magnesium in 100.0 milliliters of 3 molar HCl. Now there's a set of information here that we're gonna have to collect. So for example, we have in the lab manual that the density of the solution is 1.050 grams per milliliter, and the specific heat of the solution is 4.9166 joules per gram per degree Celsius. Okay, we have a few things that we've determined. For example, in the previous part, in this particular set of data that I showed you, we arrived at an average heat capacity of the calorimeter of 22.6 joules per degree Celsius. Okay, that was our data, not yours necessarily. And we saw, although I don't have it right here, that the initial temperature was 20.5 degrees, and the final temperature, as estimated from the graph, was 38.0 degrees Celsius. All right. So I'm going to walk us back here to, again, our doc cam. And let's look at that data again. And let's see what we can do with it. All right. So remember that the data that we have in here, the density and the specific heat, these are all in your handout here in your lab manual. You can see them over here towards the lower part of page 37. You can see it there. That's where the data came from. All right. So let's see what we have here in this system. All right. So remember again, the total heat that is exchanged in this reaction would be whatever the reaction put out plus whatever the solution put out plus whatever the calorimeter put out, or exchange probably is a better way of determining it, of saying it. And remember that according to the conservation of energy, this should be zero. There should be no net exchange of energy inside the calorimeter. Whatever one component lost, another one must have absorbed so that the total thermal energy stayed constant. So let's rearrange this because our interest here is in the heat of the reaction. So that would be the negative, if we pull everything to the side here, of the heat of the solution plus the heat of the calorimeter. All right. So we can do this several ways, but to make it simple, let's calculate each one of these independent. So what would be the heat exchange for the solution? Well, it would be the mass of the solution times the specific heat of the solution times the temperature change for the solution. So that would be, what is the mass? Well, we don't know, but we know we have 100 milliliters and we have the density. So 100.0 mLs at a density of 1.050 grams per milliliter. That cancels out the mLs and gives us the grams. The specific heat is 4.9166 joules per gram per degree Celsius. And that knocks out the grams. And the temperature change, final minus initial, is 38.0 minus 20.5 degrees Celsius. They're at the end. All right. So if we make this calculation here, let's see. Tell you what, let's go ahead and make it over here. I have my calculator here. So we have 100 times 1.050 times 4. Well, hold on, let's do that again. Let's do my calculator is a little simple. Oops. So 38 degrees minus 20.5 degrees, 17.5, that's 3 sig figs, all right, times 4.9166 times 1.050 times 100. So that's like 9,034 point something, but we're pushing the sig figs here. So this would be roughly about 9,034 joules. Notice that all of the other units cancel out. Now let's see what would be the heat exchange for the calorimeter. So that would be the heat capacity of the calorimeter times the temperature change for the calorimeter. We established in the previous experiment that this would be 22.6 joules per degree Celsius. And the temperature change for the calorimeter in this experiment would be the same. Since the calorimeter and the HCl solution were sitting there by themselves, they basically should have started at the same temperature. And because of the time frame in which we do the experiment, they should have ended up at the same temperature. So this should also be 38.0 minus 20.5 degrees Celsius, which means the degrees are going to cancel out. So again, 38 minus 20.5 times 22.6. That's about 395. We're going to round it up to 396 joules. All right. And so the heat of our reaction would be minus the heat of the solution, which was 9034, plus the heat of the calorimeter, which is 396. Notice that both of these are positive because the solution and calorimeter should have absorbed the heat that was released by our exothermic reaction. Okay, so 395.5 plus 9034. So that should be essentially 9,430 joules when you round things up. All right. But here's the important thing. This is the amount of heat that was produced by our reaction. Oh, don't forget the negative sign there. Sorry about that. Under these conditions, delta H, which is actually what we're looking for, the enthalpy change, which is essentially the heat of the reaction at constant pressure for 1 mole of our reactant. Now, in this case, we had an excess of HCl so that whatever amount of heat is here is generated with magnesium being the limiting reactant. So we can simply calculate how many moles of magnesium were in there. So this is going to be the heat of the reaction divided by the number of moles, in this case of magnesium. Now remember, if your data was for calcium, that would be a different value in there, okay? So this is going to be minus 9,430 joules. But we typically do enthalpies in kilojoules per mole. So let's convert this into kilojoules. So 1 kilojoule is 1,000 joules. And we have 0.4817 grams of magnesium and 1 mole of magnesium. So we need our periodic table, which should be out here somewhere. Oh, here it is. Have your periodic table ready. I circle here magnesium and then calcium for those of you doing calcium. So the molar mass of magnesium is 24.31. 24.31 grams of magnesium. So that cancels out those. The joules will cancel out here. So I think I'm just going to basically say that delta H here, I'm going to do the calculations. It's approximately about minus 476 kilojoules per mole. Remember, this number is delta H1 in our path of reactions for the Hess's law application, all right? What do we do next? Well, the next thing you'll do is you will take the data for the reaction of the metal oxide. Let's say in this case, magnesium oxide, okay? And then what you'll do is you'll do the same set of calculations for the oxide and find out what was delta H for the oxide. That is going to be delta H2, all right? So let's go back to our assembly or our ensemble of reactions here that we did initially. Remember that what we did was we said that in this process, we make a fictitious reaction path that yields the reaction we want, all right? So our final enthalpy is going to be delta H1 minus delta H2 plus delta H3. Now let's remember where these came from. Delta H3 we said is a given, right? We said that up here. That is a value that's been given to us. So that's negative 285.8 kilojoules per mole. All right. Delta H1 we obtained from the reaction of the metal plus HCl. And delta H2, we got it from the reaction of the metal oxide plus HCl. Careful, because we know that those reactions were exothermic. They had negative values of enthalpy, but don't forget, you're subtracting that one in there. So be careful with the signs, okay? Be very careful with your math. Now, once you've done these calculations, you're going to have a value for the heat of formation of your metal oxide. How well did our results compare with what is known about this? Well, you have one more task to do, all right? And that is you have to find what is the reported value, official value, of this delta H of formation of your particular metal oxide. So that could be either magnesium oxide or calcium oxide. In the instructions, we tell you what are some possible places where you can go, Appendix 2B of your TRO textbook, or you can Google it. Whatever the source is, please make sure you write down where you got the value from. And then what you're going to do is you're going to calculate your percent error. Now, one of the things that sometimes is troublesome with our lab manual is that they sometimes kind of mix up terminology. Let me see if I can find the data sheet that you're supposed to be doing here. Here it is. At the bottom of the data sheet, don't forget, you need to write down what is the actual delta H of your metal oxide. Don't forget that, all right? In other words, don't leave it buried in your calculations where nobody can find it. Make sure you put it in here. And now it says here percent deviation. You know, we've been calling that the percent error. And you should know by now what is the formula for calculating that. So you're comparing the value you obtained versus the value that the literature says it should be, and you're going to calculate the percent error. And again, it should be, you know, hopefully no more than 10% off of what the reported value is. That's kind of typically our goal. All right. So that's essentially our experiment. And once you have done all these calculations, don't forget, you still have to put together your full lab report. Your full lab report consists of, number one, your pre-lab outline. Then you have your data sheet from your calibration data that you were provided with, all right? But you had to fill in the values at the bottom of that sheet, right? The calibrated heat capacities and the average. There are 3 graphs that go with that part of the experiment. Then you had the data sheet for the reactions of the metal and the metal oxide with the acid, all right? And then a graph for each one of those. And then your calculations that you had to submit also. All of that together is your lab report. So my recommendation is don't wait until the due date to start working on this. Start immediately. Give yourself a few days to work on it. Give you a chance to kind of like come in fresh every time. Maybe split it into sections as you do the work to make sure that you do a good job. Remember that this is really the perhaps the most important practice you're going to have in terms of calorimetry in preparation for our exam number 2. And so I want you to take full advantage of it. And again, if you have any questions, something's not working out, you don't understand something, again, don't hesitate to contact me. You can email me, or you can send me a text message, or you can message me through Canvas. All right. I want to thank Dr. Perot for her help with the videos, and I want to thank you for your efforts that you're making. And it's my hope that you will enjoy this activity. All right. So we'll see you soon, and hasta la vista.